Hello, good evening. Hi, Audrey. How are you?
Hello. Hi, Patrick. Thanks for your invitation.
Thanks for joining. Thanks everybody who is joining. I think people we are still joining on the fly. I'm super excited to welcome Audrey tonight for this event. We have been talking for a while now to have you here. In general, the purpose of Pi and AI in Darmstadt events are to really talk about AI application for space system design, also in manufacturing, testing, but operations. So we had guests talking about anomaly detections in spacecraft operations already, also in vision-based navigation. Today, we focus a bit more on NLP side. So we try to cover different aspects of AI applied to space. Today, for this particular event, I'm super happy to welcome Audrey, who has a PhD from Strathclyde University that she obtained, I think, this year or last year, right?
Recently, December 2021.
Oh, okay, really nice. And she recently joined the European Space Agency as a research fellow, but I'm sure she's going to explain it a bit better than myself. So I will let you introduce yourself.
Okay, thanks, Patrick. Thanks again for the invitation. I've put the chat on my other screen, so I'll try to see from time to time if anybody has a question. Otherwise, just try to interrupt me. Don't hesitate. So I'm here today to talk about a family of models that I developed during my PhD called the SpaceTransformers. And but before we get into the topic of space transformers, I just want to first introduce you a bit to my background and my motivation to do some research in NLP and to try to bridge NLP with space systems. Then for the people that are not too familiar with NLP and transformers and attention, we'll have a few slides to explain to you simply in a high level way what this is about. And then we'll dive into more of a domain application, so the space transformers. And then at the end, I also have a bit of kind of like thoughts about where I think NLP could be heading for space. And then, of course, you're very welcome also to contribute to what are your thoughts about this, especially if some people are working in space and they want to exchange about potential application that they can actually see for NLP. All right. So first of all, so I'm French. So my background, I have first a diploma in general engineering, and I have a Master of Science in Aerospace Engineering from the Royal Institute of Technology, KTH, from Stockholm. So early career, so I was really into space systems. So for my early career, I started with a young graduate trainee at ESTEC. So ESTEC is the technical heart of the European Space Agency, and we're based in the Netherlands. So I did a young graduate trainee. Is actually a program for people that just graduated, and you get to spend 1 year at ESA, so you can get to different sites of ESA. So it's really good because it helps you kind of understand how ESA works, and then often you can go back then to the industry, and it kind of it's a bit of a springboard for your career. So actually, I think they are open right now, the young graduate trainee opportunities, and they are closing very soon. So if there are some students, you can check them out on the ESA website. So I did my young graduate trainee with future missions of Earth observation. And actually, I stayed on board after the young graduate trainee as a contractor. So I stayed on around 3 years in this team. So while I was there, one of the tasks I had to do was to help review proposals for Earth explorers. So Earth explorers are research missions that are designed to address key scientific challenge. So here there are 2 examples of Earth explorer missions. I did not work on them. These are just examples. So on the left, you have SMOS, which is assessing the salinity, the sea surface salinity of the ocean. So you have an example of an output of a data obtained with SMOS below, where you see the different level of salinity in the ocean. And on the right, you have Aeolus, which, as the name indicates, is used to monitor winds. well, probably it's probably a more scientific way to say it, sorry. But yeah, so you have an example of an output of Aeolus, which is you can see the wind in meter second apparently around the pole. Anyway, so this is just to say that during my time, my first time at ESTEC, I was more involved into the early stages of space mission design. And this is when I really started to realize, and it really hit me, that the design of space mission is still today really heavily based on documents. So it's true that we're trying to move towards model-based system engineering, MBSE, but still we have accumulated a lot of documents in the past decade, of designing a spacecraft. So why is that so? Well, it's because the mission life cycle is divided in several consecutive milestones in different design phases. And each phase comes with its own review and its loads of documentation. For instance, feasibility study reports, mission requirements document, or system requirement document. So why is this a problem? Why should we care? So we've been accumulating a lot of information, and at the start of my PhD, I did just this survey with some ESA experts that are involved in early phase of mission design, and we quickly realized that actually these experts are spending a lot of time searching information. So it means that your engineers are not wasting, but they're like taking a lot of their time just looking for information because we have so much documents that have been accumulated and it's not structured properly. So yeah, so this was kind of my motivation to start to look into AI and especially NLP, so natural language processing, to understand how this could help facilitate, let's say, knowledge reuse and support decision making, and also increase maybe design processes of space missions. So yeah, so I embarked on a PhD at the University of Strathclyde in 2018. And so my thesis is named Text Mining and Natural Language Processing for the Early Stages of Space Mission Design. It's available online. I added a QR code as well. It's a short document, 250 pages, but so if you're interested, I've tried to make it so that engineers could also pick it up and understand. I will try to make the AI part accessible to engineers because I'm an engineer and I kind of like discovered AI and I had to kind of start from scratch with NLP during my thesis. So I wanted to make sure that this could be like taken by engineers as well. And so I finished the PhD recently, and I was not completely traumatized by research, so I decided to continue. And now I'm doing a research fellow. Again, I'm back at ESTEC in the Netherlands. So this is a bit my motivation. So a space system engineer who try to see how AI could, help her colleagues design mission faster.
Thanks, Audrey. Yes, and maybe I can also complement a bit on this aspect. It's true that even when I worked in the industry, I faced this exact challenge that you mentioned, where you have to generate an analysis, or to make some computation for an analysis report, and you are looking for some key information that are that it's an input to your analysis, and you have to find out which documents contain this input. Is it actually the last update, because we have a lot of updates? So it's not an easy task with all of the documents we have, and yes, indeed, we spend a lot of time.
Yep, yeah, and very often it's very similar questions as well, like the number of time as a WGT where you're asked to review all the available platforms or the available launchers. Like it's like, okay, maybe there's a better way, like or to make our life easier.
Yes, yes, and sometimes we also feel bad about asking all of the people around us. So if this can be some helper to use NLP, this can be great.
Yeah. Actually, I will talk of a precise example about that just a
Okay,
bit after about heritage analysis. Actually, yeah, I'll try to remember to make the link here. Yeah.
sure. Thanks.
So, just a bit of introduction to what is NLP and what are transformers and attention, because transformers and attention is quite recent. It's kind of like at the moment the most recent methods that we have in the field of NLP. So I don't expect everybody to know about it. So NLP, it's basically the branch of AI that studies how machines understand spoken and written natural human language. As you know, human language can be very ambiguous. Like we have sarcasm, we use metaphors. So it can be really hard actually for a machine to really understand the meaning of a sentence. That's why it's not a very straightforward field. So natural language processing is usually divided in two branches. So on one side, you have NLU, natural language understanding, which is basically everything which is about the machine understanding the language. And this is divided between syntactic analysis and then semantic analysis. So syntactic analysis will be everything that is like the grammar, detecting that a verb is a verb. So what we call part of speech tagging, POS. And then maybe using regular expression to then define a pattern. Okay, when you have a subject and you have verbs and you have object. And then on the other side, you have a semantic analysis, which is more attached to understanding the context. So, and you will find more like machine learning techniques in this sub-branch. And on the other side, something I did not explore during the PhD, but that I'm really interested into is the natural language generation. So yeah, generating data, generating text, like for summarization or even complementing a sentence or else. So there are a lot of daily life application of NLP. Well, the most common one always cited is the spam filter. Then you have language translation. That's I use a lot here in the Netherlands. Then you have search results. So with the semantic analysis, the search engine can more and more better understand our queries, and therefore you have better and better answers to your queries. Of course, you have a smart assistant, so Siri, Alexa. Ones that I find quite interesting, the sentiment analysis. So, for instance, taking customer reviews or even like student feedback and just trying to detect the sentiment behind, like automatically is this person more or less happy with the service or so on. And then one that I use quite a bit as well, sentence completion. So I guess maybe you have this in your email when you're writing your email, and then it suggests like a end for your sentence. Sometimes it's really on the point. Often it's very, very well on the point, and that's quite useful. Then I just want to say quickly, I have other space applications that I did during my thesis that I'm not going to get into detail here, but I just wanted to give an overview very quickly. So one of the first things that I did was try to build an ontology from text. So why do we need an ontology? An ontology allows you to structure the knowledge and therefore to enable semantic interoperability between various sources. And also in my case, if you use it combined with a knowledge graph, you can enable autonomous reasoning. So building an ontology is what is I should say that an ontology is basically the description of all the concepts and relation found in a universe of discourse. So for example, you have a satellite, which is a concept, and it's linked to a launcher, and the relation satellite is launched on board the launcher. Anyway, what I wanted to say is that we used NLP to discover concept. So we used word embedding. So a word embedding is a method that takes a word and maps it to a vector that represents the word, the context of the word. And here on this figure, so you can see that we have projected in 2 dimensions various vectors representing different words. And this helps you actually to cluster these words in concept. So I don't know if you see my mouse. Do you see the mouse?
Yes, we can see it.
Okay. So here you have a kind of a propellant cluster. Here you have a frequency band cluster. So these are just terms. And with the word embedding, you can cluster them in concept. And that helps you to build your ontology. Another thing that was quite interesting, that was a probabilistic method. So it's topic modeling. And topic modeling finds hidden topics in text. So you can give a book to your model, and the model will say, okay, this book is about this topic, and this topic. So we used it to learn spacecraft topics. So we used it to learn what propulsion topics looks like. So a propulsion topic, for instance, is represented by several words. So electric propulsion, ion, and so on. And we used it to basically automatically understand what were the topics of requirements. So then you can use it for categorizing requirements and handling requirements, because spacecrafts are complex systems. So they come with hundreds and hundreds of requirements. Maybe I'll just quickly, I'm not spending too much time on this. Maybe it's a bit too much, but you can find it in the thesis, and also don't hesitate to ask me questions afterwards after this. The last one that I thought was quite interesting is heritage analysis. I really like this application. So when you start a mission, one of the first thing you do is that you look if there are any past missions that are similar. So you can maybe see what design was used before, which components were used before. It can help you really kickstart the study. The thing is, how do you know which past missions are similar? And I was working with a team at ISA that actually what they would do is that they would go see this senior engineer, and they would ask him, hey, I have this mission, which mission is similar? And of course, this guy had been here for a few years, and so he knew immediately. But now this person has actually retired. So, they cannot directly go and ask Andy for a solution. So, but you could turn instead to AI to give you a first idea. So how would you do that? What you can do is that instead of embedding a word, you can embed a full document or chapters. Let's say chapters. And then you have a vector that represents the chapter. And you can compare your vector to other chapters or so on to find missions that are similar. So, but if you have a new mission, imagine you can enter like a description of your objective or of the metadata, and then you would have a vector that represents your objective, and you can project it into a space, a two-dimension space if you want, and maybe see if it clusters, if it's close to another mission. So this is what we did. It's working more or less. It had some interesting results, but yeah, I just gave you an example. So we had a mission for, let's say, mission X, and we saw that its mission analysis was very close to mission A and speaker mission. So I think that's actually that could be a very promising path for NLP application. I would like to refine it furthermore. Okay, and additional applications, that I did not talk about, but I see very often, and I think people can relate to, is Simon. So Simon is a crew interactive mobile companion. So it was developed by the German Space Agency, DLR, with IBM and with Airbus and with a German university. And Simon, so right now, it's a picture of Simon on the International Space Station with ESA astronaut Luca Parmitano. And what Simon does is that basically it's a flying chatbot. I mean, it's an astronaut assistant. It has autonomous flight capacity. So if you tell it go to the Columbus module, it will go to the Columbus module. And take pictures there autonomously and come back to you. And then it can support scientific experiments. So when an astronaut is doing an experiment, usually they have a booklet with like procedures to follow. But what they can do instead is that to have like, if their hands are busy, obviously, like not doing the experiment, they can just indirectly talk to Simon and Simon can answer. And finally, Simon is also studied to be emotional support for crews for long duration mission that we are planning to Mars and beyond, to see, you know, because obviously there will be like some, well, I'm not a psychologist, but I know there will be like there's a lot of work done to see the psychological effects on long duration cruise. So Simon could be like a bit of a little Tamagotchi, like being a emotional support to kind of also understand, analyze the sentiment of the crew, see how they're feeling, if they're feeling down, and provide emotional support. All in all, so this is interesting because when we're gonna explore beyond low Earth orbits, communication with ground control are gonna be more and more prevented by the communication delay. And so today, astronauts on the ISS, they have a luxury of kind of being able to call Earth whenever there is a problem or if they have a question. So they have a lot of on-ground support. So we'll not have this luxury when we travel farther. So this way it's important to have also maybe this robotic support that can answer experts' questions and support the missions. There are also a few design assistants. So design assistant supports for mission design. So one of the teams that I made during my PhD was developing Daphne, a virtual assistant, I would say, for Earth observation mission design. And this team is based at TAMU, Texas A&M University. And also there is a startup, Vision Space Technology. I should have put their name, but they are developing Karel AI, which is an assistant more for operation of complex systems. And they are based close to ESOC, so in Darmstadt. A few applications that I think I've already seen for NLP would be requirement verification and traceability. Also using, I know there's work done to try to detect novelty in proposals. So you get a proposal through, for instance, the OZIP platform. OZIP is like a platform where people can suggest studies to ESA. And so when you have a new proposal, you need to see, okay, is this like a novel proposal? Is this worth it? Or have we already worked on this? So again, this is useful if you can have an AI that tells you, okay, like this is new, this is innovative, let's go. And for the ontology, merci. Thank you, Jean-Luc, for the link. Also, yeah, ontology definition, we are starting work now at ESA to help support the definition of the first space system ontology, which is currently done manually. It's been launched in 2019. And we're looking into seeing if NLP could support this development. And then trend detection. So NLP, like topic modeling, can help also survey trends in the space field and try to detect new trends. And finally, reports generation. I think that's a bit the dream of a lot of engineers to to just have to click a button and then they will not have to write a report. So we're not there yet, but I've seen a few. I mean, there are some ideas and there are a few, let's say, model-based system engineering systems that offer reports generation features already. Right, so that was just the first introduction into NLP, how NLP is currently applied in the space field. So now I want to get back to more of a research aspect, what has been done, what has happened lately in the NLP field, because we've seen a big revolution in this field, a kind of a massive breakthrough. And this all started in 2018 when Google AI language released Bert. So Bert stands for bidirectional encoder representation from transformers. So I know it sounds a bit cryptic when you don't know what transformers are or what bidirectional is. So we're going to take it step by step. So first of all, Bert is a language model. So it's a model which learns the probability of a sequence of words in a language. So basically, it's a model that could complement, that could tell you if you say the red fox jumps over the, and the model could suggest barrier with a high probability. So Bert made a lot of noise because when it was released, it advanced the state of the art, the SOTA performances on 11 NLP tasks, among which question answering, named entity recognition, sentiment analysis. Named entity recognition is when you have a text and you're trying to automatically extract named entity, for instance, ESA, Airbus, or city names, etc. So Bert is based on the Transformers architecture. It's going to become clearer in the next slide. And it was trained, the model was trained on 2 self-supervised training objectives. The first one is masked language model. So masked language model is when you give a sentence to your model and you mask one word and you let the model guess the word. So that's how you train it. So if a model guesses right, you're like, yeah, good. If it doesn't guess it right, then you have to fine tune again your weights. And we call it a self-supervised task because that's what's brilliant about it is that you don't need to have a label corpus. So it means that you can just give text and the model is gonna mask the word itself, and it will also know which word is behind. So you don't need to provide a label data set. Yeah, I hope yeah. And then the second task it was trained on was a next sentence prediction. And this is basically you give two sentences to the model and you say, you ask the model if 2 sentences are, follow each other or if they are not related at all. So Bert, when it was released and it exploded basically the SOTA performances, it kind of triggered a lot of interest in the field, and then it also triggered a tsunami of models that were based on a similar architecture. So very soon after, you had Facebook AIs that released Roberta for robustly optimized Bert pre-training approach. We got a few domain-specific models, SciBert, which is a scientific Bert. One of my favorite, obviously, Camembert, a tasty French language model. So same as Bert, but trained on French content. Albert, BioBert, Pattern Bert. So people also have to make an effort to find a funny name, has to be like a play on words or or at least indicate the field of the model. So why is Bert so special? So first of all, it's trained on a very large corpus, 3.3 billion words. That's a lot of data. So this is general data though. So it's like book corpus, English Wikipedia. So that's general content, so not domain specific. Secondly, Bert provides contextualized embedding. So it really takes into account the context. What does it mean? Previous embedding methods like word2vec would take one word like spring and would just give you one embedding for spring. But spring can be a season. It can be a water, spring of water, I think. It can be also, the elastic, a spring. And Bert is capable of making the difference between these 3 words. So Bert can really understand that there is that the same word can have different meaning. And that was quite a breakthrough. Bert is truly, and one of the reasons is because Bert is really bidirectional. So it can learn on both a surrounding of your words, so the words that come before and the words that come after. So again, it has a deeper sense of context. And it relies on several layers of attention. I will explain what attention is. So all in all, what you need to remember is that Bert produces high quality features that you can reuse for another task. And this is what actually made what we call transfer learning mainstream for NLP people, I guess. And fourth, which is important when you're a PhD student, it's open source. So actually, that's also explained why people were excited and really started to use it. So let's take it step by step because I introduced two things. So transfer learning and attention. So first, what is transfer learning? Transfer learning kind of existed for computer vision, but it just arrived, let's say, in NLP. So the idea of transfer learning is that you have a model that you train on a first training objective. We call that pre-training. And then you apply this model to other target objective. We call it fine-tuning. So Bert was trained on this model, on the mask language model, and on the next sentence prediction. Okay, so Bert ends up with so being trained on that, on a massive corpus, which is unlabeled. And then you can take Bert and you can fine tune it for question answering task, for sentiment analysis, for concept recognition, for anything you want. And for the fine tuning, you don't need a big data set. You just need a small data set. And that was really the breakthrough, because in a lot of, let's say, at least for domain specific field, we struggle with access to labeled data sets. So now we have a very powerful model, and it gives you amazing performances, and you don't even need a big data set. So that's really like a key enabler. So transfer learning, taking advantage of what has already been trained to apply it to your specific task. I hope that's clear. Is that what? Is that clear, Patrick?
Yes. I think
yeah.
so. Imagine I'm working in a big space system company. I can download one of these language models that has been already pre-trained by somebody on a general corpus of text. Then I could fine-tune it on my own company data, a specific task, which can be named entity recognition, and that's would enable me to save some time in generating data for named entity recognitions, because it has already acquired some general English knowledge, for example, right?
Yeah, exactly. Yeah, that is perfect.
And one other question: if I so I'm working in this like big company, and we have a lot of in-house text. Can I improve again these models with my own company's language? And specific documents?
That's exactly what we did. That's SpaceTransformers. But you
Oh, amazing.
So that's what we called further pre-training.
Oh, right.
Yeah.
Good.
Yeah. I don't know if we coined that. No, I think somebody else already used that word. But yeah, further pre-training.
Good.
Yeah, that's exactly. So I think somebody said, can you explain how SQUAD works? SQUAD is the Stanford question answering data set. So it's just used as a benchmark. Basically, it's around 100,000. Well, the original was 100,000 question answering pairs, and you can use it. Basically, it's already a labeled data set that you can just use and to evaluate your model, basically. But there's no domain specific equivalent, of course. So that's just for general data sets. And can this model be used to analyze the pre-launch condition for a space mission? So you would mean to kind of the launch condition, like the weather, the weather conditions?
Yeah.
No, the pre-launch condition, like no, go ahead. I'm not sure I understand.
Yeah, I think there can be many types of conditions. So it can be probably based on procedures, conditions that people have to manually check if every condition is satisfied. But maybe if you can, Arvind, if you can elaborate a bit more on what you think, that could be helpful.
Trajectories, fuel. Yeah, I mean, when I think, for instance, of Daphne, the design assistant, they do a Pareto analysis. Well, not really a Pareto, but they're able to kind of plot, depending on several conditions, what would be the best design choice. So I guess it could be like an equivalent for this. I'm not exactly sure which parameter it would be, but for sure, yeah. You can definitely use machine learning anyway for prediction and so on. So that's for transfer learning. So that's there's been a breakthrough in the field. And so I said that maybe I will go fast on this one. So Transformers. So basically, Transformers was at the wait, I'll do another way. So Bert is based on the transformer architecture. The transformer model was introduced in this very important paper by Vaswani and all. It's called Attention is All You Need. So the transformer is a sequence-to-sequence model, which is only based on attention. So I know attention is still mysterious, but just bear with me. So the transformer is basically you give it an input sequence and you have a stack of encoders that are going to encode your sentence. Imagine if we are in a case of a machine translation, language translation. So you give it French, above it encodes, you get an embedding, the contextualized embedding, and here it goes to the decoder, and then the output would be the translated French into Dutch. So what's important, what happened is that the transformer was released. Okay, Vaswani all, they said, okay, we use attention in the transformer. And then the Bert team, they said, okay, we're going to take the encoding part, because with the encoding part, we get contextualized embedding. Roughly, huh? Roughly what happened. And what is attention? So attention is a big word for a weighted sum. So an attention head can look at a sentence. For instance, let's take this one. So we look at two sentences. So the spacecraft was launched last month and it is now orbiting the moon. So the attention head will come and will say, okay, we're looking at this target word it. And I want to pay especially attention to a subject-verb relationship. So it is. Another attention head will say, okay, my job is to look more into pronouns relationship. So it is related to spacecraft. So it means the spacecraft. So what it allows to do, each attention head is kind of looking at different components of your sentence. So it means that you can play with the different relationship of your target word, of the target word with other words. So it can really help amplify the signal from different parts of the input sequence. So you have several heads in parallel, one layer, and then you have another layer with other heads. So the more you go, the more you go through the stacks of attention head, the more you're going to start paying attention to different parts of a sentence, and you're building your contextualized embedding from that. And why do I say it's a weighted sum? It's basically because you're paying more or less attention, you're giving more or less weights to different words of your context window. And yeah, in this example, actually, there's an open source tool. I put a reference at the end that allows you to input a sentence and kind of play and see the different weights given by your attention head. And the stronger the line, the stronger the weight. Yeah, so attention is just a way of doing the embeddings that basically you pay attention to different parts of your sentence. So help you really create a very contextualized embedding. But it's just a weighted sum. Oh. When you look into the math, like you're like, okay, it's a cool name. Yeah, I want to say just a word. I don't know if there are any questions about attention and transformers and Bert.
Not at this stage.
So then I just want to say a word about GPT-3. So GPT stands for Generative Pre-train. And this was developed by OpenAI. One of the founders is Elon Musk, I think. Yeah. And what they did is like they took the decoder part of the transformer architecture. So Bert, is based on the encoder part. So this one is based on the decoder part. And they trained a monster. So they made GPT-3 has 96 layers with 96 attention heads. There's an embedding size which is enormous, and all in all, you end up with 175 billion parameters. So Bert is more in the frame of like 3 million, million of parameters, but this is like really a step above. It's we're talking billion parameters. And it was trained on like an enormous corpus, like around 40 gigabytes with a cluster. I don't even know the actual number, a cluster of GPUs. But I wanted to talk about GPT-3. So I've not used it, but it's just that we've seen it a lot, I think, on social media, because a lot of people were playing with it, just giving it a sentence, and then GPT-3, or at least the previous generation, GPT-2 already, was creating a text, and then it was saying horrible stuff, because actually this is trained on like general online content, and you have a lot of well, you know, what you can find online is not has a lot of bias. So actually there was a lot of let's say bad comments about the previous generation, saying that they were extremely biased, and that we should be extremely careful with what they were generating. And actually, well, they even decided to not make it open source, technically saying that they wanted to avoid people making fake content, which is interesting as well. But it is actually, it's available if you pay for it. But now there's a playground, so they have a OpenAI playground, and you can play with it, which I did. So for instance, here I gave it a sentence. I gave a model a sentence. So the astronaut hears a noise coming from outside the spacecraft, and in green, this is what the model generated. So she goes to investigate and finds a small creature with a big head. The astronaut is curious and decides to take the creature back to the spacecraft for further study. I thought it was actually, it works pretty well. I mean, it makes sense. I mean, I don't know if it really makes sense, but if it's a good idea, but yeah. So that was, and also it's interesting because you see like it used he, she, so it's trying to be gender neutral. So that's pretty good. And then there are a few applications you guys can try. You just need to register to OpenAI, and then you can have different applications you can play with. So for instance, write a tagline for a rocket, and then the model says, the sky is not the limit. Or you can convert movies titles in emoji. I know I was a bit diverging here, but so I enter Interstellar, and then it gave me like a galaxy and a rocket, so it was pretty good. Maybe something more related to space mission design. So this is text summarization. So I gave the model this description of a spacecraft Aeolus, and I asked it to summarize it with this too long, did not read. And this is the output that it gave. So actually, it's kind of like a paraphrase of this second sentence, but it's still pretty good. So I guess that would be useful, you know?
Yeah,
And that's also, yeah.
For sure, that's, I'm sure, is really helpful for many people who needs to review very long documents, and or just have an idea of what's inside, and want to get a quick overview when they don't have time to read it. So for sure, text summarization can also be very powerful. Yeah.
Yeah, and also what's impressive is that this is not even a domain-specific model. It's just trained on general data. So it's pretty good that it already gives you like kind of like answers that make sense. But I did try, they had a question answering also playground, and there the model was not able to answer domain-specific questions. So I asked how many spacecraft were launched in 2021? So it could not answer. I asked, okay, who is Elon Musk? It could not answer. So, so yeah.
Okay.
Doesn't, but still, so it's funny. It's like, it shows you a bit, but it shows you the power of GPT-3 and of transformers in general. But there are still some limitations. I think maybe what we're talking a bit about in the NLP field is that what we are observing is just an exponential growth of parameter. So here you have Bert, which has, so the large version of Bert has 340 million parameters. Then Roberta arrived with 355, and then GPT-3, you know, it's not even on the, it's, at least I think I have GPT-2. Yeah, it's here. But so basically what's happening is like some companies are just training like larger and larger model. And of course, if you train with more attention head, or with a larger corpus, of course, until at least for now, it has worked that you get better performances and that you beat the previous model. But there's a bit of a question of like, until where can we go like this, you know? And I really like this paper, actually. I recommend that you have a look at it. Energy and policy consideration for deep learning in NLP. Because actually training these models have a financial and an environmental cost. So I think the authors, they said actually that training Bert's base was the equivalent of like a trans-American flight. And this is like still a baby model compared to what we do now. And yeah, and also, so there's an environmental cost of having all these GPUs running for days for training the models. And honestly, there's also a financial cost because I think like training GPT-2 was like a few tens of $1,000s, but I think GPT-3 was like, we're talking more like of the order of magnitude of like millions of dollars. And well, this is something that not everybody can afford. Like as a researcher, it's like you're way over your head. So yeah, so there's also like there's a counter trend in the field that is looking at like trying to achieve similar performances but with smaller models. So for instance, you have Bert or even Albert, which is a lighter version of Bert. Also, just a side note, so Bert has a maximum sequence length of 512, which means that if you want to ingest larger content, bigger content, you need to have a bit of tricks, or you need to break down some text into smaller batches, which means that maybe sometimes you lose a bit of context, but that's just a side note. Okay, so I guess we took a bit of time, but I hope now that you understand more what transformers are, entangenies, transfer learning. So now we can actually talk about space transformers. Okay, so the motivation. So as I say, Bert was trained on general corpus. And in the literature reviews that we've done, we've noticed that domain-specific model, they perform better than generally trained models. I'm talking for domain-specific tasks. So we've noticed that this is the case for the medical field. So you have a clinical Bert. Also the case for the legal field. Just as a side note, by the way, the medical and the legal field are really, really advanced in NLP. So they really, there's a lot of research for NLP in this field. So I was always bumping into their studies when I was doing my literature review. So I think we could take also inspiration from what they do for seeing that it works for them. So we could definitely like spin it in the space field. So our idea, we just took 3 available models, Bert, Roberta, and Cybert. And we further trained them on our domain-specific corpus. So we didn't fine-tune it yet. It was a bit what Patrick was suggesting before, is that you take your model and you say, hey, I got more documents for you to look at. And they happen to be domain-specific documents. And yeah, look at them, train on them, and adjust your weights, your contextualized embeddings, so they become, so they integrate this domain-specific dimension. And to evaluate the model, we use the concept recognition task, because to evaluate your transformer-based model, you need to use a fine-tuning task to see how it performs on a task. So the first challenge was, we thought, okay, do we want to actually train from scratch, or do we actually want to further pre-train? The reality is that, as I kind of hinted before, training from scratch is super resource intensive. Like Cybert was trained 7 days on a TPU. TPU is a tensor processing unit. It's more powerful than a GPU. It requires a lot of data. And just also in a, not philosophical, but I mean, in a strategical point of view, maybe it doesn't make sense to start from scratch. You know, you're better off just taking advantage of all the knowledge that a pre-trained model has already ingested. So, you know, you're kind of like, your model already knows how to speak English, and now you just need to teach it space systems, yeah. So that's why we decided to further pre-train. It's not like we had the choice to train from scratch. We didn't have the resources anyway. So, but you know, we're like, oh, well, actually, maybe that's even better anyway. So one of the challenge is to collect domain-specific data. I'll say a bit more after that, and also to get access to label data, so for the concept recognition task, and again, the computing resources. So for the, actually I will go first, yeah. So for the corpus, what I did as a first part of my thesis is that I went and collected as much data, unstructured data, so books, publication, Wikipedia article related to space systems. So, and then I use this kind of data set, this space system data set, to apply all of my different methods, all of the methods I studied during my PhD. So once again, we use this data set. So it represented around 360,000 sentences, mostly from books. And we use them, this is the corpus we used to train the Bert. So it was around 15, it represented 15 gigabytes of data. So what we did is that we took this corpus on space system, and then we took the weights from the pre-trained model. So, and we created Space Bert, Space Roberta, and Space Cybert. Voilà. And then for the fine tuning, we used a data set, ECSS. So ECSS is the European Cooperation for Space Standardization. So we use ECSS requirements. And we used our model to find concepts in these requirements. So here are example of requirements. So make it a bit less abstract. So an ECSS requirement is you find them in the ECSS standards, and they are basically each standard basically include several requirements which briefly describe a regulatory provision in a customer supplier context. So basically, when you design a mission with ESA, you have to respect the ECSS standards, and you have to comply to the requirements found in the ECSS standards. So as example, you have here, the supplier should provide the test report for the reviews as agreed with the customer, or the polarity test shall be one of the last tests before shipment to the launch site. So what we try to do is that we wanted our model to identify concepts such as supplier, test report, polarity test, space segment. So that's what you want your model to find. So to fine-tune your model, you need a label data set. So actually, we had a master student called Paul Darm, who was in charge of defining the labeling schema. And we focused on spacecraft subsystem and also on the different ECSS branches. Yes, I have the labels here. So you found all the subsystem of a spacecraft, power, structure, GNC, and also things that are related to the requirements, to the standard, sorry, so quality control, safety and risk control. And so we label, well, mostly Paul, label these requirements using Prodigy. So here you have an example of how he labeled this requirement. So it's pretty good actually. So you have it's a good interface because then you have your requirement and then you can select which label you want to assign to this concept. And he created, and then we also confirm let's say we double check the labeling. And in the end, we had for each label, you had around from 100 to 300 labels. So actually, in the grand schema of how machine learning usually works, this is not so many labels, right? So that's good because it works, yeah. So transformers, again, the Bert model, the transformer model don't require large label datasets. For the further pre-training, as I said, so we had access to one NVIDIA V100 GPU, which is hosted on a supercomputer that we have access to called ArchiWest, that we have access to at the University of Strathclyde. And then we use the Hugging Face library and the Python transformer library. So if you're into transformers, definitely you should know Hugging Face. Hugging Face, they're really facilitating, let's say, the training, the further pre-training of models. And they also have a very large library of models. So, and you can just call a model with their API. So it's really, it's perfect. It's really good. And it's made by, actually the founders are French. So don't know why. It's not really important, but they're French. Yeah. And these are the results. So let's say you have the initial models of Bert, SciBert, Roberta, and then our model SpaceBert, SciBert, and Space Roberta. So what you can notice is that actually Space Roberta is the most performant. So I've highlighted in green the best F1 score, and below is the standard deviation. So Space Roberta actually was the most performant model. The difference between Roberta and Bert is that Roberta was trained on larger corpus, it used larger batch sizes, and it doesn't use masked language models. So it's no, it doesn't use next sentence predictions. So it's just focusing on masked language modeling. So yeah, so that was the main output. Space Roberta was the most efficient model. And also, so by the way, also we did in the paper you can find there's statistical. We demonstrate the significance of the results, so with a statistical analysis. And here, actually, on this figure, so you have, let's say, the difference between a simple lookup approach, so just looking for label concept, doing a control F search in your requirements, and the prediction done by Space Roberta. So as you can see, the model was able to extrapolate and discover labels that were not seen during the training and that were found in the validation set. So it means that this is actually pretty successful model and in finding in labeling the requirements with, again, a small label dataset. So in conclusion, well, all the further pre-trained model outperforms their respective baseline model, but definitely Space Roberta was the most performant and the highest ranking. And the statistical analysis, well, definitely showed that maybe the training further training was not that beneficial for SpaceBert or SpaceSciBert. We're not sure really why, but definitely Space Roberta, at least, has been the most performant. And here I have a link, so you can find actually our model online in the Hugging Face library. And it's kind of cool because I know already a few companies and researchers that have reused Space Roberta. So it's quite gratifying as a researcher when actually you can actively contribute and people actually use your model. Looking ahead. So just looking ahead for what's awaiting, let's say, NLP for space. Well, first of all, there are a few trends in NLP. So there is explainable AI, which I think is really interesting. So explainable AI is just a branch which is trying to make AI not a black box anymore, but trying to have the model justify the outputs. I think this is going to be extremely important if you want engineers to accept AI in their design process. The model should be able to explain how it got to a certain result, and just saying that it's a black box is not good enough anymore. Then you have a few shots and zero shots learning. So this is a new type of training where you give really a limited amount of training data to your model. So again, all these 4 points I haven't done yet, but this is just like the trends that are that you can see starting to emerge that you should maybe be aware of if you're interested in this field. So this is going to be amazing because, I mean, when you think about it, maybe your way of approach, having to label data sets is quite primitive. So if we can find a way around that and just have a few things to label and then off you go, the model understands, that would be perfect. And then multimodal models, that's cool. That's a model that can extract information from, let's say, both text and images. So that's interesting because in your documents you have a lot of also images and figures. So if you could extract information from that, you would gain more. You would retain more knowledge. And also multilingual model, so a model that could understand both, let's say, English and French. So that could be cool because then you could like get information on design from different agencies or from different sources, and you can really have maybe an international point of view on space mission design. And just there is a model called MUM, MUM, by Google, and they just so it stands for Multitask Unified Model, and it's able to it understands 75 languages, and it's also able to extract information from both text and images. So this is, it's already kind of there. I don't know if it's open source. I don't know. And for NLP for space, what I hope is that it will have really an increasing role throughout the mission life cycle. So being used for design, being used for, I don't know, throughout all the phases, and also in operations. So you can think, of course, like report summarization, report generation. We don't need to write anything anymore. Requirements verification, also in complement with like MBSE. So maybe having the semantic understanding to understand a requirement that is written, and then checking if the design is how to say well, complies with the requirement. And then hopefully I hope to see active design assistant, so they will be able to do a heritage analysis super quickly, flagging design flaws, and also conversing with engineers and suggesting design options. And maybe also what I'm interested into at the moment is combining NLP with knowledge graphs. So you can use NLP to build the structure, the backbone of a knowledge graph, and therefore, as I say, enable autonomous reasoning. And just the little limits that I see, access to unstructured data is, whether it's labeled or unlabeled, is really hard still because of the knowledge hoarding, and also so people not really keen on sharing the data, either because sometimes they don't know if it's confidential or if there's going to be a problem with the authors, and also just data scattering, that maybe sometimes the data is not centralized, so everybody has their own data set. And yeah, also having AI being accepted, so changing the current processes. So basically convincing engineers and users to rely on an AI tool. I think it's normal that every time you have a new tool that you need to justify that it's valid tool, that it's an accurate tool. So that's where I think XI, explainable AI, will be key. And finally, I just put handling bias because I'm not too sure. Yeah, bias a bit tricky in this case, because I think I talked a bit to Patrick about that, because I was like, I'm not sure if bias. I know it's a big thing in AI, avoiding. Well, maybe it's something that makes more sense when you touch to something is more human. But for the design of missions, I don't know yet if actually we should be careful about bias. Okay, maybe we're like overrepresenting a certain type of satellite. Does this have an impact on the overall design? But this is something actually I don't think I've seen much work on it. Yeah, a few references, and then that's it for me. But really, we have some time, and we could have an open discussion. And I'm open to your feedback.
Thank you.
I will also turn the light.
Thank you very much, Audrey. It was really a very interesting presentation. I've shared also a few links to the papers, the thesis, and way to follow the work. So I'm seeing some questions. So yes, people, if you want to ask questions, you can feel free to ask them in the chat. If you want to take the mic as well, please let us know or jump in. This can be also a nice way to interact. Right now, I work with MATLAB, Simulink, and Python. How can I learn NLP AI? Like the systematic way to learn NLP. Yeah, maybe that can be an interesting question to you, Audrey, because you say you have more an engineering background. How did you learn all of this?
Actually, they were with deep learning on the Coursera. There are a lot of very good online classes that you can take. Yeah, so it was also a bit of just trying. So there are a lot of libraries in Python, like for instance Gensim or again Hugging Face that you can use. There are plenty of tutorial online. But I would say a good way to start is definitely Coursera and the deep learning courses. They're really good. And they
Yes.
happen to organize this event, but it's not even related. I really believe so.
Yeah, no, it's not really related, but I can also share the link to the courses here in the chat. I think if you're not really in general familiar with deep learning, the deep learning specialization is great to start with. And then when you want to focus on NLP, the NLP specialization is also good. I've done both, and I can also recommend it gladly because it really helps. Yeah, Matthias is saying thank you. A couple of people have already left, but they said it's a really interesting presentation, so I'm really happy. Then we have a question. Is there a risk in open sourcing sharing models that were fine-tuned on classified informations? For instance, if a model was fine-tuned using a set of classified mission reports, will there be any chance that the fine-tuned model will leak classified data in any form? I think that's an interesting question.
Yes, that's good. Yeah, it's a good question. For instance, like our Bert, our space transformer model, we did not. We had some additional documents that the CDF, so the Concurrent Design Facility team of ESTEC, had given us, but we didn't use them in the training of our models. Not also because we had to train our model on the supercomputer, so we didn't want to risk having to store it anywhere, storing the data where we could not control it. But I think it would depend, yeah, on what you fine tune the model for. So I wonder if you fine tune it for like a text generation or text summarization. I think there is a risk somehow that your model will kind of take as an example a sentence that would be maybe classifying information, but maybe it would be like an extract of a sentence. I don't think somebody could reverse engineer a spacecraft from contextualized embedding. I don't think so, because the embedding is built from really different, so many different sentences that you're not gonna, if you just do concept recognition, you're not gonna end up with very secret information coming out. Maybe I'm just wondering, actually, how much if you were doing text generation, how much that would be impacted by the content of the training set.
Yeah, indeed. Okay. Yeah, thanks for this answer. We don't have other answer, so maybe I will take a chance to ask one. In the beginning of the presentation, you mentioned topic modeling, and also to train Space Roberta, you mentioned a set of topics. How did you define that? How did you started with, to have these categories?
Yeah. So for Space LDA, so we're just targeting the categorization of mission requirements, and these are usually organized per subsystem. So we just took common subsystem, and for the transformer model, so what Paul started with, he started also by looking at the ECSS branches, and the ECSS are also organized per topics. And well, roughly. So we extrapolated based on that and based on the ESA and the NASA taxonomy. But I think we were trying to kind of still try to find, well, at least the interest one is again trying to reach out to branch to the spacecraft subsystem.
Okay. So in the end, this shows also a bit how the subject matter expertise is still required in running some of these AI projects.
Yeah, I think, at least from my in my case, it was a strength also to have a space system background. because I had maybe more ideas of what was relevant with my little limited experience, of course, in space system. But I mean, I still had maybe a better idea as somebody that would just have a computer science background. So I think that's why it's important that it comes from also engineers from different fields, that they take interest into AI and that they actually try it out. And you can definitely still learn. I think anybody can always learn at any point of their, in the stage of their career. So yeah, when it comes from a domain expert, it's good because they can directly see maybe applications and maybe the points or the bottlenecks that they have encountered.
Sure. Is there any other question? I think we still have a few minutes in case. So if somebody has some question, please feel free to ask. It's going to be one of your last chance. But of course, you can still, I guess, reach out to Audrey by email, and she might be happy to answer.
Yeah, of course. And I saw there were a few people from the University of Strathclyde, so that's cool.
Nice. Yeah, it's nice to see some names here and there that we know.
And I mean, definitely Jean-Luc could tell you more about how the ECSS works and about the ontologies at ESA. No, but yeah. So because at ESA, yeah, they are trying to define the first. They are defining the first space system ontology, the European space system ontology, and when this arrives, this will also be very interesting. Because this will allow us, I think, for me, it will allow to merge more data in a knowledge graph, and then will unlock a lot of knowledge. Looking forward.
Yes, we are also looking forward for this cooperation. So the ontology is a huge endeavor to try to classify all the terms that we are using in space. And with a specific language, which is called ORM, that we are using, we have really a formal way to organize our knowledge. So I think that together with NLP, I think we can do miracles. We might need a couple of years to achieve this and to have it practically applied in space. But I know some projects with some industry, they are starting to use it sometimes in their projects. So it is very promising, and congratulations, Audrey, for this presentation. It was awesome.
Thanks, Jean-Luc.
Thanks, Jean-Luc, for your input. Great. Anybody else before we wrap it up? So I think your presentation was very well received. People thank you a lot, and I would like to thank you a lot for giving this presentation. And yeah, I think it was really really helpful to see a practical way to apply all of these buzzwords, but in an industrial setting and at the European Space Agency, and also in a university, because I think most of this work was done at University of Strathclyde. Please check out the links that we shared in the chat if you want to learn more. So to the attendees, you can also follow the future events of Pi and AI Darmstadt, which are all AI events dedicated to space applications. You can follow them by following the Rocket AI LinkedIn channel. And if you want to watch replay of these events or future ones, there is a Rocket AI YouTube channel as well. So I'm going to paste again the links here in the chat, so you can all follow and stay tuned in. And yeah, I think it's time to wrap it up. So thank you very much.
Thanks for organizing this. It's a really good event.
Great.
No, thanks to you.
So I wish you a good rest of the day or evening, or depending where you are in the world. So thank you, everybody, and see you next time.